In section 6, we're talking about the reactions of ethers. Ethers are fairly inert, and they're useful as solvents for organic chemistry reactions. The only way to really react an ether is to treat it with very strong acid, hydrogen bromide, hydrogen iodide, possibly hydrogen chloride, but that's less efficient. Now, ethers will react by cleavage reactions. And so you need to add excess acid. We'll just use HBr here. And what you form here is 2 alkyl halides and water. So those R groups can be primary, secondary, or tertiary. Okay. If it's primary, it's going to occur through an SN2 reaction. If it's tertiary, the reaction mechanism is going to proceed through an SN1. Okay? And if it's secondary, it can occur through either. I don't think anybody will fault you if you choose SN1 instead of SN2. And the book actually doesn't have questions on those because there's no set answer, okay? All right, so come back to that page. Okay, so let's take a look at the reaction mechanism. Let's take diethyl ether and treat this with excess HBr and explain how 2 equivalents of bromoethane and water can be produced. Okay, so in this curved arrow reaction mechanism, we want to first protonate the oxygen. And I'd like to point out here that we have a carbon atom that's primary, and here we have carbon atom that's primary. So in the next step, bromide can sufficiently do a bimolecular nucleophilic substitution on that primary carbon. So bromide is the counter ion from hydrogen bromide. We can use some curved arrows to show how a neutral oxygen is the leaving group. So that's one equivalent of bromoethane. Now, ethanol can react with excess HBr. Let's put a little excess in front of that. So if we have HBr here, I'll show the acid-base reaction like this. HBr will react to give you an oxonium ion. Bromide can attack that primary carbon, displace neutral water, and give you bromoethane. Okay, so this is where water is formed. So water is a reaction product. That's where the oxygen ends up. And so you form 2 equivalents of bromoethane. Why 2 equivalents? Because your symmetrical ether has 2 of the same ethyl groups. Now, if you have an ether like this reaction would still react with excess hydrogen bromide to give you 2 equivalents of the tert-butyl bromide and water. Now, because this is a tertiary carbon, this is going to occur through SN1 reaction mechanism. So let me just briefly highlight how that would occur. We once again protonate the oxygen. There's an oxonium ion intermediate, okay? And what we want to do now is form the carbocation. So we want to directly depart our leaving group here to form tert-butyl alcohol. and our carbocation, which is a tert-butyl carbocation. And then bromide is going to attack this to form tert-butyl bromide. This alcohol can, proceed onwards by protonating, okay, to give you the oxonium ion intermediate. Okay. Water is a sufficiently good leaving group. And again, this is an SN1 process whenever you have a carbocation being formed here. You form the carbocation intermediate just like above. Bromide attacks, okay, and you form the second equivalent of tert-butyl bromide. So when you have tertiary ethers, they react by SN1. When you have primary ethers, those react by SN2. Now, the only other thing I want to point out is when you have phenyl ethers, and these react very specifically. So if we have, let's say, ethyl phenyl ether, and we treat this with, let's do HI this time. What you're going to form, and we're not using excess, what you're going to form is a phenol. And your alkyl halide, in this case, is going to be iodoethane. So that part we're kind of familiar with, but here we stop. And the reason why is because this carbon here is sp2 hybridized. And there's no SN2 or SN1 chemistry that efficiently happens on sp2 hybridized carbons. Okay, and we kind of learned about that back in chapter 6 or 7 or whatever chapter that was. So the reaction mechanism is quite standard. You protonate the oxygen of your ether to give you that intermediate that has a positive charge on oxygen. We call that an oxonium ion intermediate. Okay, and then I minus is going to prefer to attack the primary carbon. Now, it doesn't matter that this is secondary. What really matters is that is sp2 hybridized, so we cannot have a direct nucleophilic attack on that carbon atom. So what happens is the iodide attacks this carbon, kicks off phenol as the leaving group, and that's where the reaction stops. Okay, so that's how the reaction mechanism occurs. You have SN2, but only on the alkyl carbon, okay? Alkenes, arenes, or aromatic carbons do not participate in SN2, okay? So let's do that problem 14.11. Predict the products for each of the following reactions. So we don't need to draw the curved arrow reaction mechanism here. We just need to analyze things. Those two carbons that I'm dotting in part A are primary carbons. So what we're going to form is a primary alkyl halide on the left, and that's a symmetrical ether. So that's the only product that we're going to be forming. And of course, we form water. Okay. In molecule B, we have a cyclic ether. So watch out for this. Each of those two carbon-oxygen bonds are converted to a carbon-iodine bond. Okay. So what we're going to form in B is one molecule that has an iodine at the beginning of the chain and another iodine at the end of the chain. Okay, so I'm dotting those carbons and we'll form H2O. Okay. In molecule C, this is a phenol, so let's use a different colored pen to emphasize that. This right here is going to be one product, and then the other product is going to arise from those two carbons. So we're going to have a phenol on the left and an alkyl halide on the right. And it's going to be bromine because HBr is a source of bromine. Okay. For molecule D, it becomes even more complicated. This molecule here is a phenol. So this is the bond that's going to be broken here. I'm trying to dot this line. Now, there's a carbon-oxygen bond there that's going to be broken, and that's where the carbon halogen is going to be introduced. And then the oxygen aromatic bond does not break. So what you're going to do is break only that dotted line there, okay, that bond. So you're going to form a phenol, okay, like this. But you still have this carbon bonded, and this carbon bonded. And now I want to attach a halogen to that carbon atom, okay? So that's where the iodine is. In molecule E, we have a tertiary carbon on the left. That's going to be transformed to a carbon halogen bond. We have a primary carbon on the right. That's going to be transformed to a carbon halogen bond. So the molecule is going to look something like this. Okay, where I have an iodine here and an iodine here. And remember that since this reacts by SN1, you're going to give a racemic reaction mixture. And so the other product we can have is going to be where those two groups are inverted. So methyl group, propyl group. Okay, and I got our halogen here. This is not looking very nicely drawn. And an iodine. Okay, so this stereogenic center is converted to a planar carbocation, and the iodide could attack that carbocation from the top face or the bottom face, giving you the R or the S isomers, okay? In molecule F, this is not a phenol, okay? This is not a phenol. So we have two groups. We have a cyclohexyl group, which becomes cyclohexyl bromide, or bromocyclohexane, if you will, and bromoethane, okay? And of course, we form water. I'm not drawing water in all of these. Okay, so that's it for this problem. I hope that makes sense. You might have to read the book and review a little bit, maybe work through the curved arrow reaction mechanisms if you have trouble deciding which carbon-oxygen bond is being broken, what halogen goes where, and where does the oxygen go, okay? So thanks for watching.